Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video kind of rounds out the graphs of polynomials, of polynomial functions section within a college algebra course. Now, if you're in pre-calculus, you'll notice there are a few topics missing, like the rational roots theorem, stuff like that. But that's not the purview of a college algebra course, at least at our college. So this is sort of a spiral method where you're introduced to smaller topics gently and then grow those topics over time into pre-calculus when you get to use those bigger theorems. Instead of just diving into graphs of polynomial functions here, I'm going to start with just understanding the relationship between the degree of a polynomial function and the number of turning points that polynomial function has when it's graphed. So the theorem is stated right here. A polynomial of degree n has at most n minus 1 turning points. I'm not going to prove this, I'm going to justify this. So let's take a look at a polynomial of degree 1. So for example, we're taking a look at a polynomial function p sub 1 of x, which may look like, let's say, a negative 3x plus 1. Why not? So it looks something like this. I didn't plot any points or anything like that. I just know it's a line with a y-intercept at 1 and a slope that is negative and somewhat steeply negative. So I just scrawled out something very quickly. Now, notice this does not all of a sudden turn. So there's 0 turning points here. And it's a degree 1 polynomial. So degree of p sub 1 is equal to 1. And yet the number of turning points that we can see is just going to be 0. So number of turning points equals 0. We can see it on the graph. It doesn't turn around. However, if you grow this to be something like, I don't know, p sub 2 of x, which is equal to, let's say it's just x squared minus 4. Let's just deal with that one. So again, that's a parabola using our transformations. It's shifted down 4 units, so it might look something like this. And that function has degree 2, so I'll write that in here. Moreover, if you look at the function itself, there is a point where it turns. That point is right there. So it has a single turning point. And if you think about all parabolas, they do have a single turning point. So this kind of is convincing, at least, that a degree 2 polynomial has at most 1 turning point. Now, where this sort of falls apart is when you get to third degree polynomials and higher. Because I could just quickly scratch out 2 different third degree polynomials. Let's say we have p sub 3. I'm not going to give you the function because, well, I don't want to make one up, to be honest with you. But this one, let's just pretend is just y equals x cubed, or p sub 3 of x is equal to x cubed. That's a third degree polynomial, yet there are no turning points with this. There's no point when it's rising and then falling. I didn't actually define it, but a turning point is a point on a function where it goes from increasing to decreasing or from decreasing to increasing. I might as well just write that down so we have it. So a function, which in this case I'm assuming the name of the function is just f of x, a function has a turning point at a comma f of a if the function switches from increasing to decreasing at that point, or vice versa. It can switch from decreasing to increasing. So if you look at our parabola, it switches from decreasing to increasing at this blue dot point right there. And so that blue dot is considered to be a turning point. Now, to be very honest with you, as you advance through mathematics, nobody really says turning point. If they do, they're kind of teaching lower level courses. That's not exactly what we'd call them. We'd call that an absolute, or sorry, a local minimum. or we call them local maximums. But that's not the purview, again, of the college algebra course that we teach at our college. We saved that for pre-calculus, so we'll just call them turning points right now. But going back to this example, we have a third degree polynomial, and notice it does not switch from increasing to decreasing at any moment. So the degree of p sub 3 is 3, but simultaneously p sub 3 does not have any turning points. However, that does not contradict the theorem stated up here. The theorem says a polynomial, let's just insert 3 for n, a polynomial of degree 3 has at most 2 turning points. And that phrase, at most, is very important, because if I said I have at most $2, that means I could have 0, 1, or $2. 0 is perfectly fine because 0 is at most 2. So it's okay that we have a third degree polynomial that does not have a turning point. But I can create a third degree polynomial, so I'll call it p sub 3 bar, that does have 2 turning points. This is still a third degree polynomial, and it has 2 turning points right here and right here, local maximum and the local minimum. So it is true that you can have 0 turning points or up to n minus 1 turning points for an nth degree polynomial. So let's take an example here. And this example, I'm pulling together ideas from videos that you should have seen already in this series, specifically identifying zeros and their multiplicities. I'm using something from that here. But this question is asking us to state the possible degree of the polynomial function represented by the following graph. Now, if you take a look at the number of turning points, that helps out. There's 1, 2, 3, 4, and 5 turning points. That means that this polynomial, if you only looked at the turning points, this polynomial would have to be at least 6th degree. So I'm going to zoom in and just state that. So by the number of turning points, which is 5, this polynomial is at least of 6th degree. However, I did sneak something else in here. So if your instructor just kind of scratches something out without having some isolated behavior, specifically this behavior right here, then you can just count up the number of turning points, add 1, and that's the minimal degree of that polynomial. However, let's include a little bit of the conversation we had from a previous section. So if you look at this root right there, that's probably multiplicity 1. Here's another multiplicity 1. Here's another multiplicity 1. This is likely multiplicity 2. I'm going to write M2, M1, M1. I'm just going to do that so we keep track of what I'm saying. And this guy right here is likely multiplicity 3 because it looks like a cubic when you zoom in. And so if I really thought about not only the turning points, but just looking at the zeros as well, you'll see that the multiplicities all add up to 2 plus 3 plus 1 plus 1 plus 1, or 8. So this polynomial actually has a degree at least 8. Now again, they might not be asking for that level of detail, but it is actually true that by considering the behavior near the zeros, this polynomial is likely of degree 8. Now I'm going to zoom out because the next example is going to ask me for a possible formula for this function. In fact, I'll just show you. That's exactly what I'm asking. But I'd like to not answer it on this page. I'd like to keep the graph in front of me while I answer. So let's just answer here. Now, I didn't label any points, and because I just made up the graph. So let me label some points. Let's suppose that this is x equals negative 12. This might be x equals negative 6. So this might be x equals negative 3. This might be x equals positive 4. And that might be x equals positive, let's just say 10. So a possible function or formula for this polynomial would be the following. And this assumes that you've watched the previous videos on zeros and their multiplicities and using factoring to find zeros of polynomials, and knowing how to identify end behavior polynomials and all that other fun stuff. I happen to know that this polynomial will have some type of lead coefficient, which I'll just call a for now. And it has a 0 at -12, so I know that x minus a -12, or x plus 12, must be a factor. Again, that's from a previous video, I think the one right before this. -6, x equals -6 is also, right there, is also a 0. So therefore, x minus a -6, or x plus 6, must also be a factor. Again, the multiplicities on these zeros, 1 and 1, that tells me that the powers on those factors are also 1 and 1. The next 0 occurs at -3, so x minus a -3, which is x plus 3, must also be a factor. Again, first power because multiplicity 1. The next 0 occurs at +4. And that's the most interesting of the zeros, because if +4 is a 0 for this function, then x minus that +4 must be a factor. And because it's multiplicity 3, sorry, my wrist hit the screen there. Because that 0 is a multiplicity 3, the factor will have a third power upon it. And finally, 10. X equals 10 is a 0, so x minus 10 must therefore be a factor. Its multiplicity is 2, so therefore the power on the factor x minus 10 must be 2. You don't want to leave it like this for several reasons. First, because you don't know what a is and you'd like to state at least a ballpark idea of what a could be. And second, nobody would actually leave ones in the exponents. They would just write, for example, the x plus 12 to the first as just x plus 12. If you write the 1 there, it's a little elementary. It's not what you want to do. It's like somebody saying, somebody probably could say, I have 1 car. But I don't know. You just don't want to use the 1 is usually silent in language, and so therefore you want it to also be silent as an exponent. So how do we approximate that leading coefficient of a? Well, you use the end behavior here. Since it's going down on the left-hand side and down as x goes to positive infinity, we know that this is going to act like an upside down parabola, so therefore we need a negative as the leading coefficient. Now you can make up any value you want that's negative. I'm just going to write -1/100th just because I want to. The rest of it I just copy without the ones on the powers because they're silent. There's no reason to write those in there. So the entire polynomial, when everything's written out properly, is this guy right here. And again, your leading coefficient could be any other number as long as it's negative. And now we get to kind of the final moment with graphing polynomial functions and really dealing with polynomial functions in a college algebra course. As I mentioned previously, if you're in pre-calculus and you're watching this kind of as a review maybe, you know that most of the polynomial functions you're going to be handed in pre-calculus will not be pre-factored like this. You will have to be able to factor them yourself. And that involves some very fancy theorems, the rational roots theorem, that type of thing. Some people use Descartes' rule of signs. I don't, but some people do. Anyhow, but in college algebra, most of it will either be pre-factored or you will be handed something that's easily factorable. So let's go ahead and talk about this bad boy right here. Graph this function, p of x equals yada, yada, yada. The first thing you're going to do is state the zeros, and then you're going to state their multiplicities, and then you're going to state the end behavior of this function. Really those three things. I'm going to write that down kind of as a step-by-step process. So the first thing I'm going to write are the zeros. And the second thing I'm going to write are their multiplicities. I guess multiplicities. I should have said the second thing we're going to write is, but it doesn't matter. Okay, so if you look at the zeros, I think a lot of people would easily see that the 3/2 is a 0 there and a -4 is a 0 there, because that's what turns those two factors into 0. But a lot of people often miss this guy. That turns into 0 when x is 0. So the zeros that we have are 0, 3/2, and a -4. Again, because those are the values of x that will turn each of these factors right here into 0. And that's kind of why they're called zeros, honestly. And the next thing you're going to do is right below those, state their multiplicities. So for example, the power on the factor of x minus 0, or the power on x itself, is just 1. And the power on the factor of 2x minus 3, that gave us the 0 of 3/2, is 3. And the power on the factor of x plus 4, which gave us the 0 at x equals -4, is 6. So it's pretty simple if you have things pre-factored to state the zeros and their multiplicities. And then the next thing you're going to state is the overall degree of the polynomial. And that is just found by adding up the multiplicities. It's the same thing as saying, I will have an x to the first from here, and eventually through multiplication of this junk right here, I'll get an x cubed. It'll have a coefficient I don't really care about, but it'll have one. And then once I multiply all this stuff out, I'll get an x to the 6th and some other stuff. But when you multiply everything out, you'll get an x to the 6th times an x to the 3rd times an x to the 1st, or an x to the 10th. But I could have avoided that entire conversation by noting 1 plus 3 plus 6 is 10. So that's what I'm going to do here. I'm also going to erase my messy handwriting. Now, the last thing you should probably note is which way is this polynomial opening? In other words, talk about the end behavior. So I'm going to note that the leading coefficient here is positive. I don't care that it's what number it is, and often it'll be too difficult to find. So it's much better just to say the leading coefficient is positive. And the reason why I know that is because look at all the leading terms, like the 1/2, I should say leading factors there. There's a 1/2 there, there's a 2 here, there's a 1 there. If you multiply all those values, since there's no negatives involved, the leading coefficient, which will be the coefficient after you multiply all those things together, with their powers, by the way, will be positive. So I know that the leading coefficient of that polynomial, had I wanted to multiply it out, would be positive. And it's degree 10, so I happen to know that this whole entire polynomial will look like roughly y equals x to the 10th power in the long run, which tells me the end behavior. The end behavior acts like x to the 10th, and we know x to the 10th, that looks like a parabola. Therefore, as x tends to either plus or minus infinity, the y values grow without bound towards infinity. All right. And remember, infinity is not a number. It is a concept. All your arithmetic kind of breaks when you deal with infinities. I try to tell that to my calculus students as often as possible, but it still kind of falls on deaf ears by every once in a while. So let's go ahead and graph this out. We might have graphed this in a previous lecture, but I don't mind graphing it twice. It's not that big of a deal. Draw in an x-axis. I'm not going to bother with the y-axis yet because I want to plot my zeros. So I have a 0 at x equals 0, actually. So I'll just plot a dot at x equals 0. I have a 0 at 3/2, so I'll just plot a dot at 3/2. And also a 0 at -4. There we go. So we have those all plotted out. And now that I know where the y-axis should be, I will go ahead and draw it in. It's always at x equals 0, so there we go. That's my y-axis. And now I'll go ahead and start graphing this polynomial. We do know the end behavior should be up and up. It should end up looking as we go to infinity on either the x, as x either goes to positive infinity or as x goes to negative infinity. We know that the edges of our graph should rise up to positive infinity. The y value should. So then I start graphing from left to right. That's just a habit I have. So I'll start at this arrow that's firing up to infinity, and I'll just start allowing the graph to fall because the ink wants to tend to the x-intercepts or the zeros. Now remember, that -4, it's a 0 of multiplicity 6. So that means locally near to that, and in fact, I should use blue ink. I just like blue ink better here for this situation. As that blue ink tends to the x-axis, it's going to look like a parabola, but very, very flat. It's not going to have that nice like U-shaped. It's going to be somewhat flat in there. Sorry about that. My graph just got kind of messy, but so it'll be flat for a little bit and then it'll start to spike up. And when you do this, you'll notice that your arrow might be slightly off. That's okay. That's why you have an eraser. And so you just do something like that. It still ends up being the same. And then as you move away from x equals -4, it'll rise up and it'll eventually want to curl right back down towards the next x-intercept. The x-intercept at 0 has a multiplicity of 1. That's this stuff right here. So I know that it's going to go through like a line. Let me zoom into here. It'll go like a line through that x-intercept. So I'm just going to try to target that and make it look kind of smooth. Remember, polynomials have a smooth behavior about them. And it might fire down a little bit, but the reality is it's going to want to be drawn right back to the next 0 in line, which has a multiplicity of 3. 3/2 has a multiplicity of 3. And so it's going to look locally like a cubic. Sometimes I just go ahead and pre-draw that in just to make my life a little bit easier. And it actually does kind of work in this case, so that's super nice. And then beyond there, it's just going to rise forever and ever. Now, don't worry about me missing that up arrow. That's totally okay. There's no way I could have hit that up arrow and kept it a function. So you get to erase that. It still has the same look. That is a graph of p of x is equal to 1/2 x times the quantity 2x minus 3 and quantity cubed times the quantity x plus 4 and quantity to the 6th. A common question that I will be asked by students both in college algebra and pre-calculus is, how do I find out the value of these maximums and minimums? That does get asked by really good students. They'll ask, well, does that point occur halfway between, like this point right here? Does it occur at -2? And the answer to that is probably not. The truth is that we need to use calculus to find out where that maximum occurs. So that is not where we are at right now, but in the long run, we'll get there. And so you'll be able to find those exact X and Y values for the maximums and the minimums, but it'll be a couple courses from now. All right, so that's a review, or not a review, actually, an introduction to graphing polynomial functions. It shouldn't be so complicated, and it shouldn't feel complicated. You're really looking at just what are the zeros of your function, what turns each factor into 0. What's the power on each of those factors? That tells you the multiplicity in the shape near to those zeros. So for example, x equals 0 was a 0 of multiplicity 1, and notice it looks like a line going through x equals 0. X equals 3/2 was a 0 of multiplicity 3, and so it looks like a cubic going through x equals 3/2. And then x equals -4 was a 0 of multiplicity 6, and so it looks like a really flat parabola going through there. And you do have to be pretty exact with that. Do not skip out on making that flat. When I see graphs from students that just are pretty vague with how they've drawn it, I don't give credit. I need to see that you know that the graph flattens out there. All right. Let's just try one more just because we can. And this one is only slightly different. It's actually not terrible. This time I'm just going to list things out in a table. Remember, we listed out the zeros and their multiplicities. And then once we had those two things, we were able to get the degree of our polynomial by adding up the multiplicities. And then we looked at the leading coefficient. Basically, what would that leading coefficient be when we multiply everything out? Would it be positive or would it be negative? And so I'm just going to write leading coefficient here. I don't really write out the full word coefficient because it's just a lot of handwriting, so I just stop it there. Now, looking at our polynomial, from the very first factor involving x, you can see -5 will turn that into 0, so -5 must therefore be a 0. And it'll be a 0 of multiplicity 7, because that's the power on that. The next factor that is, will occur at x equals 1, because again, 1 plugging in for x will turn that into 0, so 1. And by the way, the multiplicity of that is 1. I'll erase that. And finally, we have an x minus 10 to the third. That contributes a 0 at x equals 10, because that turns that into 0. And its multiplicity will be 3. I'm going to write that down. 0 at 10, multiplicity of 3. And now I could just, from my advice last time, just add up those multiplicities to get that the degree of this polynomial is going to be 11. And the last little bit I need to do before I can graph is just note, is the leading coefficient when I multiply all this stuff out, which I don't want to do, but if I had multiplied all this stuff out, would the leading coefficient be positive or negative? Well, let's look at this in reverse order. The coefficient of that x is 1, of that guy right there is a 1, and of that guy right there is a 1. So if you multiply all those out, you'll have a 1x to the 11th, and then times a -10. So it's actually a negative leading coefficient. I'm going to go ahead and write that in here. And now I can dive into graphing, and I can just do that actually off to the right-hand side. You don't need a ton of room for this. Also, I do want to note, you probably noticed it in the last example that, actually you probably didn't notice it in the last example because we had a y-intercept. But in this example, this polynomial, as every polynomial does, strikes the y-axis. However, I strongly advise you from not finding out what the y-intercept is here. It's because, remember, the y-intercept occurs when you allow x to be 0. If you allowed x to be 0, you would get these ridiculously large numbers. That would be massive. And I don't think that's very fair. And it'll also make your polynomial scale be really, really tough to deal with. So instead of worrying about the y-intercept, just worry about the x-intercepts, which are the zeros, and plot those appropriately. So let's see, we have a 0 at, I'm going to use blue again. We have a 0 at -5. We have a 0 all the way over at +10. And then we have a 0 at 1. So I'm going to say that's roughly right around here. That gives me an idea of where the y-axis should be, somewhere right about here. Notice that I labeled that y-axis. And then we know that the leading coefficient is negative and the degree is 11. So this polynomial will roughly look like, not exactly, but roughly look like -x to the 11th. If it's an odd degree, which it is, it'll often just look like, in the long run, a cubic. However, because it's a negative in front of it, that'll be flipped the other way and it'll look like that. So to state this rigorously, we would just say, as x goes to -infinity, y tends to +infinity. And as x goes to +infinity, the y values fall forever, specifically falling towards -infinity. So that's the end behavior of my function. Some people will be okay with you not listing this stuff out, but instead just chicken scratching out a graph so that you can see visually what your graph is going to do. Some people are okay with that. I go back and forth. It just depends. I want my students to really know that calculus notation. So I'd prefer that they say, as x approaches -infinity, y goes to +infinity. I think that's a nice thing to do. I would probably specifically ask for that on an exam if I wanted it. All right, so I know that it starts high and ends low. That's the end behavior of this. So I'll go ahead and take a look at each of the zeros. So I know it starts high, and I want to fall and approach the 0 at -5. And when it does, it's going to look like a 7th degree polynomial. So like an odd degree polynomial, but very flat. So it's going to want to look like, and notice how I do this. I spend a little bit of time near the zeros just trying to get it to be flat here. And then once you get away from that zero, it'll start rocketing up. Actually, kind of matches up with my accidentally matches up with my arrow, so that works out well. And then on the other side here, it's just going to fall. And it might fall for quite some time, but it'll eventually want to be dragged back up to hit the x-axis at x equals 1. And when it does, it'll go through like x to the first, like a line. So I'm going to zoom into that one. It's going to go through this like a line. Notice I made that somewhat steep. That's just because I see that I'm approaching from a steep angle here. So, and I might even fix that steepness as I get through. Yeah, just a little bit there. It's hard to say the steepness at that point unless you know calculus, but it's going to be steep just because it's a high degree polynomial. It's just the way of the world. So anyhow, it goes through that. It's going to rise for a little bit. It'll eventually want to be sucked right back down to x equals 10. And remember, that has multiplicity 3, so it's going to look like a cubic going through this. Let me just draw a nice, beautiful cubic going through. Notice that's not flat near x equals 10. So I'll just try to match these up if I can. So I use a lot of thick ink. And then once it gets through there, it just falls forever. And notice I'm going to miss my arrow. That's perfectly fine. I can have an eraser for that. There it goes. And we have this beautiful graph of -10 times the quantity. Well, you see it. I have the graph of p of x. Now, if you were to use Desmos here, and I do have students that copy straight from Desmos, and I give them no credit because it's incredibly easy to tell when somebody is copying from Desmos. It's actually much easier to not cheat and to know what you're doing than it is to cheat, because you spend so much time just graphing something really super quickly, thinking that you're graphing super quickly, but then not really learning the concepts. Once you know the concepts, graphing this is really easy, super duper easy. But if you were to graph this using Desmos, you'd have vertical lines. That's all you graph. And student after student does that. So just to let you know, you should be graphing these by hand. And here I am. I'm just going to drive that point home. This is that polynomial graphed on Desmos without adjusting anything with the axes. Let me move it over. I do have to zoom out slightly so you can see the intercept of 10. And as I said earlier, it'll just look like vertical lines. And that's because this is such a high degree polynomial, you can't capture the information of what it looks like with Desmos. Notice though, at x equals -5, it's definitely a flat cubic, which is exactly what we said it should be. Also notice that as it goes through x equals 1, it's like a very steep line, which we said it should be. But at x equals 10, it's not going to look like the behavior we said it should look like until we zoom in a lot. So now we see that very nice, beautiful cubic behavior here. But you don't get to see that until you scale in quite a bit here. If you just draw it from Desmos using a scale from -10 to +10, which a lot of students will do, it looks really, really horrible. Let me see if I can reset my screen. I think it's just done by there. Yeah, it looks like this, and it's terrible. I will know if you copy directly from Desmos. All right, that's enough warning for you guys. I hope everybody's doing well, and I hope that this was beneficial for you and taught you a few things.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.